recording. I'll show you where to look on that as soon as the projector comes up. Please don't let me do that. Okay. Remind me? Carla. Okay, got it. All right. Anyone else come in since I called off? Okay. I don't know of any. All right, remind me. Huh. Okay, got it. Thomas, right? Thomas, right, yeah. Okay. All right. Now, sort of hard to see from this perspective. That right there indicates it's recording. It's a little circle with two vertical lines and then a time ticking off. That means how long it's been recording. Okay. Now, get set up here. Okay. We did the first application problem, which is the iced tea can. We finished that last time. Any questions? Anything we've covered so far? All right. The one today, in honor of our crew here, the path of a baseball. Okay. So, a batter hits a baseball, dream on, okay, at a point 3 feet above the ground. Now, that's about right. Okay, let me, whoops. Name, please. Huh? Okay, got it. I can't write with that pen. Okay. Okay. About 3 feet above the ground. That's about waist high, and that's pretty much a sweet spot, right? You're a pitcher, you wouldn't know that. Okay, never mind. Okay. Are you a pitcher? Or? No, I play infield. Infield, okay. Yeah, well, you know that. Well, infield, I don't know. Okay. All right. Okay. About 3 feet above the ground, batter hits the baseball with a velocity of about 100 feet per second. Yeah, okay. At an angle of 45 degrees. Okay. Good angle. The path of the baseball is given by this function. F of x is equal to negative 0.0032. See, at an angle of 45 to get it over the infield. That's the whole purpose, right? Okay, never mind. Okay, x squared plus x plus 3. Okay, now what does that function mean? The f here, the function here, is the height of the baseball. Okay? And guess what? Okay, well, let me finish the rest of it. And that's height of the baseball in feet. Okay? And x is a horizontal distance that the baseball from home plate. And this is also, so this is a horizontal distance. Okay, also in feet. Okay? Now, when x equals 0, where are you, baseball? Home plate, right? 0 from home plate. And 0 from home plate, what is the height of the baseball? 0 here, 0 there, 3 feet. That's what the problem said. That's where you hit it. Okay? And Cole and Ryan are here. All right, good deal. Anyone else come in since I called roll? I didn't catch your name. Okay. So, this is the height of the baseball. This is the distance from home plate. And that's your function here. Now, you don't need to know where that function came from, but I'll give you a hint on a couple of things here. I've already said there's the 3, height, 3 feet when you're 0 distance from home plate. I'm not going to try to tell you where the decimal came from, but the 32, know where that came from. The acceleration due to gravity, which is affecting the height of the baseball in the U.S. customary system, that's feet per second squared, that is the acceleration due to gravity, 32 feet per second squared. That's where the 32 comes from. Now the decimal part of it, that's a little more involved how to explain that. Part of it is explained by the fact, remember, it was 100 feet per second was the velocity, but you've divided, it seems like, by that to get this to be an x, because normally the coefficient here is the velocity. So if you divide by 100 squared, that would move your decimal 4 places this way. That is very quantitative, not very very qualitative, not very quantitative. And here's Tara. Okay. And Jayla, is that right? Yeah. Okay. All right. Anyone else come in since I called roll? I didn't acknowledge you coming in. Okay. So that's just great. You don't need to know where it came from, but those are just a few clues. Okay. F is the height. X is the horizontal distance. Okay. The question is, will the baseball clear a 10-foot fence located 300 feet from home plate? So here's home plate. I'm not going to draw the baseball player because I'll just draw a stick figure with a stick in his hand. Okay. Swinging at the ball, 3 feet, 45 degrees. Will it clear somewhere way out here? That's a 10-foot fence. Okay. 300 feet from home plate. Okay. Obviously not drawn to scale. Okay. Now, that's the question. Okay. Now, how would you go about solving that? 300 feet is the distance from home plate. The question is, will it clear a 10-foot fence there? Okay. Help me with the name. Amina, right. Okay. All right. Any ideas? Good morning, Vietnam. Okay. Okay. Any ideas? 300 is the distance from home plate. 10 is the height of the fence. Okay? Give me a guess. Try it. Somebody. Help me. Say again?
Are we accounting for the ball dropping, or are we just going
Okay. Good question. You see this is a quadratic? So yes, this is from home plate. Yep. It's going to be a parabola. So yeah, we're taking care of that. The equation takes care of it. It's doing the thinking for you, almost. You just don't know how to use it. How would you use it? Good question, though. Anybody?
X is feet, right?
Yeah, X is the number of feet from home plate.
Yeah, so you're plugging.
Plug it in. 300 is the distance from home plate. Plug it in, just like Glade, right? This will be minus 0.0032 times, help me, 300 feet. I'm not going to put the units, okay. 300 squared, the X is squared, plus 300 plus 3. Don't forget the plus 3. Okay. Now, anyone know what 300? Oh, what do we do first here? You what? I couldn't hear. My hearing's so bad. Sorry. Yes, do the exponent first. Anyone know what 300 squared is? 90,000. Okay? Perfect. Okay? Multiply that by 0.0032. Let calculators help you out here. Plus 300 plus 3. And by the way, calculators are allowed, permitted, encouraged in the class. So please take advantage of them. And what do we get? Tell you one might save you some punching of zeros in there. If you move this decimal 4 places that way and move this decimal 4 places that way, that's equivalent. It's 9 times 32. Okay?
So is that negative or?
Yeah, there is a minus. I forgot to write it down. You're absolutely right. Such a messy board here. Because the reason is gravity is pulling which way? Remember I said the 32 is the acceleration of gravity? What way is the acceleration of gravity always pointing? Downward toward the center of the earth. Always. Gravity's always pulling down. So even though you hit it with an upward velocity, after a while the gravity comes down, which is probably part of your question back there. I don't know, Cole or Ryan, which one? Which? For which?
Oh, this is cold.
Cole, okay, Cole. Cole's question earlier. Gravity's pulling it down. Anyone got an answer yet? Anybody? Second? Okay, this is a negative here, but that's only that term. And you add 303. And here's Q.
Oh, okay.
Okay. Anyone get an answer yet? Second? 15 feet. So does it clear the fence? 10-foot fence? Yes, it does. Okay. And I'm even thinking infield can jump up and get one 15 feet. 10 maybe. Okay. But not 15. Okay. All right. So even bouncing off the wall, I don't think they're going to get it. Yep. Ball makes it over by 5 feet. Okay. But it was foul, unfortunately. No, I'm just kidding. Okay. All right. Any questions on that? That one's pretty simple, just plugging in a function. The function tells you that kind of stuff. Now here's another one. Any questions before I erase it? Okay. Here's another. This is alternative fuel stations. Okay. Now this is based on a graph. Okay. And graphs are not precise, they're approximate. Okay. Our calculations. Okay. Here's the graph for those who don't have your book. Okay. Now this is the number S. Okay, let me write this down. The number S, and I'm trying to figure out why they chose S here. Stations, I guess. Number S of fuel stations. Okay. That sold E85, that's a gasoline ethanol blend, in the U.S. increased in a linear pattern from 2008 until 2011. Okay, here's 2008. Now they don't write 2008, they just write 8, 9, 10. These are years after year 2000. So that's 2008. See, year 8 corresponds to 2008. So just add 2000 to this and you got the year. And you see from 2008 to 2011, it looks like close to a linear increase, okay? But then after 2011, still a linear increase, but it slowed. The slope was not as much. To begin with, a lot of stations were adding on, and then after a while, fewer stations were adding on, but still adding on. So that's what the problem is saying. Observing the data, you see this, okay? Now, then increase at a different linear pattern, 2012 to 2015, as shown in the bar graph I just showed you. These two patterns can be approximated by this, S of t. Now, the t here is year, okay? It's a time function, but it's in years. S, number of fuel stations, as a function of the year, okay? It's a piecewise defined function, because you had one piece for the first few years, a next piece for the next 2 years, few years. So the first piece was, your name please? Kayla. Kayla? Oh yeah, Kayla Stinson. Okay. All right, good deal. Any others come in since I called roll when I wasn't looking? Okay, here's one. Oh, 10 o'clock scholar again. Okay, good deal. All right. Patel is here. I still haven't figured out the best way to get here either. I'm going to try a different one next week. Because I thought left it plenty of time this morning. Should do it. Man, the lights were just miserable. The traffic wasn't bad, but the lights were just awful. So I'm going to try another one. It'll probably work because my wife recommended it. But, you know, I'll have to live with that. Okay. All right. So here we have the number of stations as a function of year. The first steep part was 260.8 t minus 439. Okay? Now, if you wonder, wait a minute, where do these weird numbers come from? Well, I showed you the graph. What you do is punch in those numbers that you read off the scale here. I'll tell you something else about doing this. See, these are number of stations, and these are 15,000, 1,500, 1,700, 1,900. It didn't start at 0 down here, but did this up to 3,100. And these, remember, were years after 2,000. So the T is the number of years after 2,000, okay, starting with 8, okay? And that's what we indicate here. This is from year 8 to year 11. Less than or equal to, including 8, including 11. Okay. Now, I was going to say, how do you get these? It's a process they call linear regression. We're not going to do that in this course. It's a statistical method of doing things, and that's how they came up with those numbers. Now, what is that saying? Remember I said those numbers over here were 1,500, 1,700, 1,900. So it's going up 261, approximately, stations per year. That's what that means. That's the slope, the average rate of increase. 261 stations a year. This is almost meaningless. This is just to make it fit the data. So that slope, if you went back to year 2000, which is an arbitrary year in the first place, you'd have had negative number of stations out. Well, that's not really true, but that's just because that's where year 0 was, year 2000. Not beginning of time, you know, year 2000. Okay, so that's what that means. That's for the first few years. Then after that, the rate of increase slows, but still positive, 151.2 times t plus 714. And again, that's sort of a meaningless y-intercept, but this is good only from years 12 less than or equal to t less than or equal to 15. So remember, this is 2008 to 2011, 2012 to 2015. That linear equation fits the first group of data. This one fits the second group. So you see the rate of increase only adding about 151 stations per year. Up here it was adding 261 stations per year. Again, the y-intercepts don't really mean much. If you had projected this line, this less steep line, let me do it this way, back to year 2000, there would have been 714 stations in. But that's meaningless. We don't know what it was in. Now, again, remember, this is a piecewise defined function, but it's explicit domain. You can't predict anything before the year 2008. We don't have the data for it. This doesn't work except for those 8, 9, 10, and 11, those 4 years. Okay? This one only works 12, 13, 14, and 15, those 4 years. So don't try to use this one anywhere else or this one. You might try to project into the future what that'll be, but who knows? The slope may have changed again. It may have gotten level by now. Who knows? Okay? So you can't go beyond your domain. Okay? Because that's what was used to come up with these numbers. Now, that's the setup. And this is approximated. Remember, if you read in the book, this, let me find that again. These two patterns can be approximated by this piecewise defined function, where t represents a year, where t equal 8 equal 2008, and use this function to approximate the number of stations that sold E85 each year from 2008 to 2015. I'm not about to do that in class today, but let's do a few. Okay? Pick a year. Any year from 2008 to 2015. Pick a year. Say again? 2010. Okay? Now what you ask yourself first, where are you, Waldo? You're at the top because 10 is in between 8 and 11. Okay? So we use this one. So you plug in, do you plug in 2010? No, you plug in 10. I can almost do that in my head. 2,608, let's multiply that by 10, minus 4, blah, 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 439. So that's going to be 21,669, all right? I did it quickly in my head. I may have messed up. Calculators slow you down, don't they? Okay. What you get? Second? 2,169. Right? Is that what you said? Perfect. See how it works? Anyone want to give me a different year? Anybody? Second? 2012. Where are you, Waldo? The bottom. Okay, this time you plug in 12 down here. You'll need a calculator on this one. I'm going to do that one in my head. 151.2 times 12 plus 714. And what you get? 2,528 stations who had ethanol or E85 in that year. Approximately. Okay? Approximately. Does that make sense? All right. You know how to do the rest of them? Knock yourself out. Do as many as you'd like just to get used to it. There is, as in all these problems, a checkpoint afterwards. You can work on that. And if you have trouble with it, there's audio-video solutions in English and Spanish at larsonprecalculus.com. Absolutely free website. No code required. And by the way, speaking of codes, I think I said this last time, but in case I forgot to say it in this class, I have requested the codes. I don't know if they've come in yet. I didn't get a chance to check email yesterday because I was in class solid from 10 in the morning until 6:30 last night. Yes. I'm sorry? No. It's just there for your viewing pleasure. And, you know, it has, I've heard, decent tutorial help, and it gives there will be exercises out there, and you can do them, see if you get the right answers. Don't let it frustrate you, but if it helps you, use it, okay? But it's all for your cultural enlightenment. Say again? Yeah, WebAssign does require a code. What I don't know is if you can access the book on, You can't. Okay, so they've changed that. The last term, they wouldn't let you access the book without the code. But if you got the book already, fantastic. Good. But I'll still give you the code in case you want to use WebAssign. All right. Any other questions on this or anything else so far? All right. Then let's move on to difference quotients. Ever heard of these before? Yay or nay? Oh, okay. A few have. Most haven't. Okay. Have you ever used one before, you think? Probably not. Let me tell you, yes, you have. You just didn't call them difference quotients. Okay? Now, what do these two words mean? Second? Difference means? Subtraction. Quotient means? Division. Okay? We're going to subtract and divide in some strange order here. Okay? Now, this is a pre-calculus algebra course, so we're getting ready for calculus. One of the basic definitions in calculus employs this ratio, or quotient. F of x plus h minus f of x divided by h. Okay. Let's see if y'all were paying attention a few classes ago. What's f of x? Y. Okay? So this is 1f at x plus h And there's a different F back there at X, so these are both Y values. This is a change of Y, okay? Now, you can't tell it from here, but let's do it this way. What's X plus H minus X? H! You're exactly right. So this is a change of X. And what's the change of Y over change of X? Change of Y over change of X. Y2 minus Y1 over X2 minus X1. Ever heard of that before? What is it? Slope. Exactly. So you have done this before. You just didn't call it a difference quotient. That ratio is a difference quotient. Difference here, difference there. You don't see the difference what it is. And then you take a quotient of it. A ratio. Division. Okay? And we're going to do that in example 11. And it will be so much fun, won't it? Okay? Here's your function. Good old quadratic function here. And it says find the difference quotient for that function. Now, what would you guess you got to do first? Say again? You may have said it. I heard. Plug it in, plug it in. What do we plug in? Okay. Okay, let's start at the beginning. Okay, how do you eat a 5,000-pound elephant?
Piece by piece.
One bite at a time, exactly, piece by piece. So let's start with the first bite or the first piece. We need to know what this is, don't we? So we plug this in instead of X, right? Okay, let's do that. So F of X plus H. What would that be?
So you'll plug it in into X squared.
Yeah, exactly. Anywhere you see an X up there, put X plus H instead down here. So what would that be? X plus H squared minus 4 times X plus H plus 7. Done. Well, way to go. Just like we did 300 last time. We just plug in X plus H here. Okay? Now we got a little math to do. Isn't that fun? Okay? Does anyone know what X plus H squared is?
X plus H
Is what?
you can do X plus H and X minus H.
No, that's not a minus. They're both pluses.
Both plus.
Okay, both pluses. So you're suggesting we write them out and FOIL it, right? Yeah, why not? Let's do that. That's the same as X plus H times X plus H. You're squaring something, you multiply it by itself. Okay, how do you do that? FOIL X squared plus, say again? Plus XH plus HS or XH. I don't care which way you do it. I do a little, not much, okay? And then finally, plus H squared. Okay, so this becomes X squared. I like the HX, so let's go back and do that. Plus how many? 2HX plus H squared. It doesn't matter which way you write them, but anyway, that's what it is. Now, you can always do that, and you got it right, you get a smiley face, right? Good deal. Okay, never mind. Now, here's a shortcut. If you like shortcuts, if you're lazy, okay, square the first number, X squared, twice the product of the two, the product is XH, double that, plus 2XH or HX, square the last number. Yeah, I don't have to write anything. I don't even have to get a smiley face. I don't care. That's what we get. It's X squared plus 2HX plus H squared. So there's your alpha of X plus H. Okay, I think we're ready to plug in now since we know the first one. So this thing will be this right here. X squared plus 2HX plus H squared. That's your alpha of X plus H, right? Minus, what's your alpha of X? Oh, there it is right there. So what's that? X squared minus 4x. Okay. Okay. And plus 7. Got it. Okay. All divided by h. I wrote something down wrong, didn't I?
Yeah.
Yes. I only did the first term. I said, this is wacko. Okay. Why did y'all let me do that? Okay. Wait a minute. I only wrote the first expression down. Okay. I forgot to write this part. That is this part. This is this part. How about this? We left that off. Minus 4x at minus 4h plus 7. All right. So this isn't working right. That's your f of x plus h. Ugh. Need a lot more room now. Minus 4x minus 4h plus 7. Whew. That's your f of x plus h. Minus now, okay, I'll write this again, x squared minus 4x plus 7, right? Divided by h. Ha, that time I got it right. But I need to clear those parentheses, so let's do that. X squared plus 2hx, I love writing these long things, plus h squared minus 4x minus 4h plus 7. Now, negate that, and what do you get? Minus x squared plus 4x. Everybody see that? Minus 7, right? And then divide it by h. All right. Now, what do you notice you can do now? Combine like terms. How many x squared terms do you see? 2. This one's a plus x squared. This one's a minus x squared. Guess what those combine to? 0. Nice. Okay, I only see one 2hx term, so we'll write that down. 2hx. I only see one h squared term. We'll keep that. How about your, oh yeah, there you got a what? Negative 4x. And a positive 4x. What do those add to? 0. Good. I didn't like that many terms. Okay. Next. Only one minus 4h. So write that down. And then plus 7 minus 7. That adds to 0. Whoo. You're left with this. Now what can you do with that? Oh, we can factor out an h. Very good. Okay. So that would be h times what's left? 2x plus h minus 4. Okay? Divided by h. And now what can you do? They divide away. And here's your difference quotient. 2x plus h minus 4. Okay? Wow. Look how simple that became. Okay? Okay. Just don't mess up like I did and forget to put the whole f of x plus h down there. As soon as I was writing, I said, this isn't working. I forgot. I left off 3 terms there.
Let
Okay.
me ask you a question.
Now,
So when you came back and added, okay, I know we broke down the, I'm gonna call it the B part of the problem.
okay, this one. No,
The other part.
this part.
Go up a little.
This
The
one.
negative 40.
Okay, this.
When we did that part and we brought it down.
Yeah.
Or we plugged it in or whatever.
Right. Okay.
Did you just bring this part over here, this x squared minus 4x plus 7 from the top?
Yeah, okay.
Okay.
Let me start over. Okay. F of x plus h, you had to plug x plus h in every term in this, right?
Right, because
Okay.
it's x.
And we did this part over here, that became this, then we did this part, that was that, and then we did that part. So this is all your f of x plus h.
Okay.
Then you subtract from that your f of x, which is this right here. And that's what we did there. Had to change the signs of all those numbers. And when you did that and start combining like terms, you find a lot of them disappear.
Right.
Now, remember we said taking a derivative. What's your name, please?
Mayfield.
Huh?
Mayfield.
Mayfield, got it. Okay. Kendria. All right, anyone else sneak in while I wasn't looking? Okay. Now, we said this was something we did in calculus. What this is called is taking a derivative. And you do a limit of this as h is approaching 0. But you can't divide by 0. That's what limits do for you. What does this get close to? The closer h goes to 0. Because guess what? As h is going to 0, this is getting closer to f of x. And then you have 0 in the numerator, 0 in the denominator. Well, that's simple. It's not undefined, it's indeterminate. If there's a limit there, this is called a derivative. Okay, it's a limit as h approaches 0. And that's what we just did. And once we divided out the h, now you can plug in h equals 0. And what do you get? If h is equal to 0, getting close to 0, this is getting close to 2x minus 4. Right? Now, for those, I hope many of you do continue and do calculus. Those who do, after a while, you'll learn the easy way to take a derivative, and that is multiply the exponent times the coefficient. 2 times 1 is 2. Reduce this by 1, 2x. Same thing here. 1 times a minus 4 is minus 4. Reduce this coefficient by exponent by 1. That gives you a 0. So this is, you get 2x minus 4. 2x minus 4. This is how we get a derivative by the limit method. We'll show you a shortcut later in calculus. Calculus 1 class isn't there yet, but you know, that's how we'll do a derivative. Exactly like that. So y'all are ready for calculus, right? Good deal. Can't wait. All right, any questions on that? Okay. Now the only trouble with what I just said, they always put this in, and it's true, h cannot equal 0. Because if it can't equal 0 here, it can't equal 0 at the end. But it can get arbitrarily close to 0, and the closer it gets to 0, the closer this gets to 2x minus 4. Okay, but that's there. So, any questions on this? There. Oh, let me erase this so you can see how they work the problem. Okay? Well, they started off with f of x plus h, that's what this is, minus f of x, that's what that is, divided by h. Okay? Now, to do this, they squared the binomial, that's what they got. They divided through the minus 4, that's what they got. They brought down the plus 7, and then they negated everything over here. Perfect. Divided by h. And then they, like you, will eliminate 0 terms, okay? X squared minus x squared goes to 0. 4x minus 4x plus 4x goes to 0. Plus 7 minus 7 goes to 0. What do you have left? 2x h. They did x h, we did h x, doesn't matter. Minus h squared minus 4h. That's all that's left. Everything else added away to 0. Divided by h. And then, just like you did, notice you can factor out an h from every term in the numerator, and that left you 2x plus h minus 4 over h, and the h's divide out, leaving you 2x plus h minus 4. As long as h is not equal to 0. There you did a difference quotient. There is the difference quotient. And by the way, that's the slope of the line, slope of the curve. Okay? It's not a line, it's a curve. It's a tangent line. Okay? Now, here's a summary of what we've been doing. Function terminology. Function is a relationship between two variables such that to each of the independent variable, the first variable in the ordered pairs, whatever you want to call it, there exists one and only one dependent variable. Give me an x, there's only one y. Okay? Here's the function notation. Main thing to remember, y is equal to f of x. Remember that. F is the name of the function, y is the dependent variable of that function. The x is the independent variable. You get to choose it to calculate the y. And f of x is the value of the function when you plug x in for the input. Okay? The domain of the function is a set of all the inputs, all the x values, the independent variable for which the function is defined. If x is in the domain of f, then f is said to be defined at x. If x is not in the domain, then you can't take a calculation there. The range is a function set of all the output values, the dependent variable values. That is a set of all function values. And then we talked about an implied domain. Explicit domain would be like the one we just did, where you had years 8, 9, 10, 11, and 12, 13, 14, and 15. Those are explicit domains. The implied domain is when the algebraic expression tells you you can't do something. And what are two things you can't do? Ever in math. You can never divide by 0, and you can't take the of what? Square root of a negative number. Perfect. Those will be the things that contribute to implied domains. Later you'll find out you can't have 0 or a negative number in a logarithm, but we haven't even gotten there yet. Okay? So those are your implied domains. That's it. Finally, for 1.4. There is a vocabulary at the top of page 44. Let's do that quickly. A relation that assigns to each element x from a set of inputs or blank set of inputs. What's that defined as? Domain. Exactly one element y in the set of outputs, which is called a range. That's called a, say again? I couldn't hear. A relation that assigns to any input one and only one output, that's called a function. Perfect. Okay. Number 2. For an equation that represents y as a function of x, the set of all values taken on by the blank variable x. What do we call the x variable? Independent variable, okay? And the set of all the values taken on by the blank variable y, that's the dependent variable in the range. Perfect. Number 3. If the domain of the function f is not given, then the set of values of the independent variable for which the expression is defined is the blank blank. If they don't explicitly tell you what the domain is, what is? Say again? Turn back one page. Implied domain. Implied domain. Last thing we did. Okay, I'll do it back here. Right here. Implied domain. There it is. Okay. And one of the basic definitions in calculus uses the ratio f of x plus h minus f of x divided by h, as long as h is not equal to 0. This ratio is a blank blank. Difference quotient. Perfect. Okay, homework exercises here. We've done most of these before, but I'll say them again. Do number 5 or 7. They're both at Calc Chat. 7's at Calc View. Do number 9. It's at Calc Chat. Do any of the odds 11 through 17. They're all at Calc Chat. 11's at Calc View. Do any of the odds 19 through 29. All at Calc Chat. 21's at Calc View. Do either 31 or 33 or both. They're both at Calc Chat. Do any of the odds 35 to 41. They're all at Calc Chat. 37's at Calc View. Either 43 or 45. Both at Calc Chat. 43's at Calc View. Do either 47 or 49. No, I'm sorry. Any of the odds 47 to 55. They're all at Calc Chat. 49's at Calc View. Do 57. That should be at Calc Chat. Do 59. It should be at Calc Chat. Then you choose any of the odds 61 through, through 71. Any of those, any ones that strike your fancy, they all should be at Calc Chat. Then 73 through 79, do any of those odds. They all are at Calc Chat. 75 is at Calc View. Do either 81 or 83. They're both at Calc Chat. And then there's a few, two true false. You're not going to see many of these on a test, but think through this. 85 and or 87, they should both be at Calc Chat. 89 probably is at Calc Chat. I kind of don't like it because they tell you right off the top it's wrong, and then tell you what you have to figure out what's wrong with it. I don't like you looking at things that are wrong. Okay, but there is some benefit in it. You can think about doing number 91 if you'd like, or 93. Okay, any questions? Second? None? Okay. So let's move on to finally 1.5. Okay. This one hopefully will go a lot faster. 1.4 had to cover everything about functions. Okay, how are we doing on time? Okay, we got plenty of time. Okay, good deal. Okay. Now, we're still in Chapter 1, Functions and their Graph. We're now in 1.5, Analyzing Graphs of Functions. Let me clue you in on something, folks. This author, this test bank, everything, they love graphing. Okay? It helps you visualize things, but I think every quiz and every test you'll ever see in this class will have at least one, and some of them more than one, graphs on it. Okay? So be ready. Get used to it. Get practice on these. Okay? So, first we're going to come up with a test for the graph of a function to see if it's a function or not. It's called the vertical line test. We will find zeros of functions. We'll define what that is. We really have already done it, but we didn't actually give that name. Okay? We'll determine intervals on which the functions are increasing or decreasing and determine relative maximum and relative minimum values of the functions. We'll determine the average rate of change of a function, and you'll discover you've already done that without realizing it. Okay? We'll get back to that. And we'll identify even and odd functions. Okay. Boy, there's an odd one. Okay, never mind. Okay. So, what do we mean by the graph of a function? Did anyone need those? Did I go through that too soon? Okay. Sorry.
Is it in the book?
It's in the book. Yeah. It's the those red bullets there right at the top of 1.5, page 49. Okay. All right. So let's look at the graph of a function. So we've studied functions from an algebraic point of view. We've talked about those that you use in sentences. We've done a few with ordered pairs and tables. But now we're going to look at it from a graphical perspective. Remember we said there's 4 ways to express a function. Now we're going to focus on the graphic. The graph of a function, f, is a collection of all the ordered pairs, x, f of x. Whoa, what were ordered pairs before? Okay, but what did we used to? Back when you graphed equations, you said x, y, but guess what y is? F of x, there it is again, okay? So this is x, y, x, f of x. Such that x is in the domain of f. It has to be in the domain, otherwise you can't plot it. You can't plug it in unless it's in the domain, okay? So, as you study this section, remember that x is the directed distance from the y-axis, the vertical axis. That's how far this way or that way you've gone. Positive in this direction, negative in that direction. That's your x. The y, which is the f of x, is how far you are up or down from the x-axis. Okay? Or you could say from the origin. Okay? So here is a graph of some unknown function, f of x. Okay? And when x happens to be this value right here, I don't know what that is, 1.2 or something like that, then your y value is right here. Alpha of 1.2, it would be somewhere here, maybe 2.1 or something like that. Whatever it happens to be, that's how you read this. When you plug in an x down here, go up to the graph or down to the graph, wherever it is, and then go across to the y-axis in whichever direction, and that's your y value. Okay? X, y plots. Only now it's y, x, f of x. Make sense? Stuff you've done before, you're just giving it a new name. F of x is y. So here's example 1. Use this graph, shown in this figure, to find the domain of f. What is the domain of that function f? Now, I'm going to give you a couple of little hints here. If you see a solid circle, that means that value is included. If you see an open circle, it means you go up to that value, but don't use that value. Okay? So what would be your domain of this function f that's represented by that graph? Domain is what?
Input.
Yes, the input values, which are on the horizontal axis, and what are they in this figure? Where does it start? From -1 to
0.
It goes past the 0,
2.
past 4. It doesn't go over here. It goes up to 5, but doesn't include 5. So how would I represent that? Second? Aha! Okay, you start with a bracket. Ooh, let me get my pen back. Okay. The domain would be, this is in interval notation. Where did we say we started? -1. It counted -1, so we use a bracket there. Okay? And it goes up to, say again?
4.
And say again? 5, but doesn't include 5, so we put a parentheses there. There's your domain. Okay, now written in set notation, you would say that domain is the set of all x's, because that's your independent variable here, x's, such that -1 is less than or equal to x, but x is less than 5. Perfect. Okay, close it out. There's how you express it in set notation. See, you don't include the 5, but you do include the -1. And in interval notation, it goes from -1 to 5, but doesn't include the 5. That's what the parentheses stands for. Very good. Excellent. How about the, now it says, what is the function values f of -1?
F of -1.
Yeah. 1, exactly. You plug in, what you put in here? X, okay? So you say you put a -1 in on the x-axis, go to -1. Then find the function, and what's its value there? 1. There it is. And it is value there. What's f of 2? All right, you go over here to 2, find the function, it's down here. What did you say it was? -3, perfect. What's f of 5? The function's not defined at 5. It's not in the domain. Okay? That was a trick question, sorry. I'm not either. Okay.
May seem a little slow.
What's that?
Go back over how you get into it.
Okay. All right. Notice how we write this. Y is equal to f of x. That's the thing I said to remember, right? So, when you put f of -1, what's that -1 in place of? X. So you get on your x-axis, the horizontal axis, the input, the independent variable, and find -1. There it is. Now you find your function. There it is. What is its value? 1. 1, -1, 1. So f of -1 is equal to 1. Do the same thing with 2. 2 is the x value. So go on the x-axis over here to 2. Find the function. There it is.
So that's when we're talking about height.
Yeah. X, y. What's it? When x is 2, y is -3. So here's the y-axis here. And that's why f of 5 is not defined. You go over here, x equals 5, and you see, it's empty. Can't do it. Empty set. No, nothing there. Nobody home. Okay. Now, next question. What's the range of this function f?
1.
Say again?
1.
The range? Okay.
1.
No, it's
Okay, I heard 1.
It's 3.
That's just a number. Huh?
3 and -3.
It goes from what? Okay. Usually you start with the lowest from negative 3 up to 3. You're absolutely right. You do the y values here from negative 3 to 3. Inclusive or exclusive? Brackets, parentheses, what? Brackets on both, because you include negative 3, include positive 3. Yes. So the range of f would be, oh, I didn't write these down. Let's write down f of negative 1. Yeah. F of negative 1 is equal to 1, and f of 2 is equal to negative 3. The range of f, a couple ways to express that. The set of all y's this time, because that's the dependent variable, such that negative 3 is less than or equal to y is less than or equal to positive 3. That's one way to express it. In interval notation, that would be bracket negative 3 comma 3 bracket. Okay, good. Get them all the pieces there. Does that make sense? The brackets indicate there's equals there. The parentheses indicates there's not an equal there. Make sense? All right. Any questions on that? Let's see how they did it. The closed dot, now they go back to their graph, and you see there is a closed dot here at negative 1, so that means that is in the domain, indicates that negative 1, 1 is, so when x is negative 1, the domain, the y value is positive 1. Their explanation here leaves a little bit desired. They're not answering the question. Whereas the open dot, go back here, at this indicates x can't be 5. 5, 2 is not included in the graph. So x equals 5 is not in the domain. So the domain of alpha x, domain of f, okay, for all x's is the interval from negative 1 to 5. Including negative 1, not including the 5. Okay? Second, because minus 1, 1 is a point on the graph, it follows when f is minus 1, when x is minus 1, f is 1. That's what that stands for. So that's its value. Similarly, because 2, negative 3 is a point on the graph, and x is 2, y is negative 3. F of 2 is negative 3. Exactly like we said, right? And then finally, the range, the graph does not extend below negative 3 nor above positive 3, but it does include both of those, so the range is the interval from negative 3 to 3. They won't always be nicely balanced like that. It just happens to be this example is. Make sense? All right, good deal. Okay. The use of dots, either open or closed, at the extreme left and right of points on a graph, indicates that the graph does not extend beyond that point. That means the domain does not include anything over here or anything past there. Doesn't even include 5, but certainly doesn't include anything past 5. It does include negative 1, but nothing past negative 1. That's what those tell you when they're at the end of the graph. Now, circles on the graph, they just say those points are included. They just happen to put this at the max and the min so you can pick out your range better. You didn't need to do that. They wouldn't have to. However, we will see occasionally a graph with a hole in the middle here. And that means it includes everything from here to there, but not that number, and then picking up just past that number to the end, whatever. So you could have a hole in the middle of the graph. Not very often, but you could. Okay, just for future reference. Okay, by definition of a function, at most one y value corresponds to any given x value, right? So picture this. For any given x value, there can only be one possible y value, right? Okay, that's the definition of a function. Okay. That means the graph of a function cannot have two or more different y's for the same x. Okay? So in other words, for this x here, there's a y. You can't have a y up here or here or here or here, anywhere else except right there. Okay? That's what it's saying here. And no 2 points on the graph. What that means, if you think about what I just said, no 2 points on the graph can be above or below each other vertically. Right? If they were, it would be a function. So that gives us a real handy way to tell whether the graph of a function, graph is a function or not. It's called the vertical line test. That observation provides a convenient visual test called vertical line test for functions. Here's what it says. A set of points on a coordinate plane is the graph of y as a function of x if and only if no vertical line intersects the graph at more than 1 point. If it does, it's not a function. Okay? Some real common graphs may not be functions. Ooh, they skipped them all, didn't they? So this is example 2. Okay? Just going to do it like this. There's a nice looking parabola, right? Is that a function? No! Because I can't hold the book up. Okay? Because for any given x here, over here, there's 2 y's, not just 1 y. Not a function. Vertical line test fails. It intersects the graph twice. Here's a real squirrely looking function. Is that a graph? Is that a function? Yes, because every point, vertical line only intersects once. How about this one? That's missing some values. Is that a function? Yes, because no vertical line hits more than one. You may have vertical lines with no values. That's okay. But you can't have a vertical line that hits twice. Okay. So that was a no, yes, yes. Okay. There is a checkpoint there. You can play around with that. All right. Now let's move to zeros of a function. And like I said, we have actually already done this, but we didn't call it by this name. I don't think so. If the graph of a function, x, has an x-intercept at a0, somewhere out here on the x-axis, the function crosses there. So the y value is 0. So from any value a where the y would be 0, that is said to be a zero of the function. That's where the function's equal to 0. So the zeros of a function, f, are the values for which f of x equals 0. Remember that set of exercises we did in 4.1? 1.4? Okay. That we were doing exactly that. We didn't say we were, but we were finding the zeros of the function. So we've already done this. So let's do a few more, since they were so much fun. Find the zeros of that first function, f. What would you do? Second? Set it equal to 0. Don't plug in 0. Set it equal to 0. 3x squared plus x minus 10 equals 0. Make the y, f of x, equals 0. Okay? You haven't found them yet, though. You just set it up. What do we do at this point? Second? I can't hear you. A little louder. Okay. You probably are saying it right. My hearing is... Okay. Now, if this was a linear function, that would be exactly what I would do. But this is a quadratic, so yes, the factor. Anytime the exponent is 2 or more, factor, if you can. Now, there's no guarantee we'll be able to factor. Okay? But let's see. If we try to factor this, what's the only possible factorization for 3x squared? 3x times x. Okay, very good. Where do we look next? The sign of the last term. What is it? Minus. That means what about these two signs? One's plus and one's minus, but we don't know which order. So this is where we call trial and error. We're going to try it this way. If it doesn't work, we'll try it another way. Now, 10. There are several factorizations for 10. Give me one. Second? 2 and 5. Let's try it that way. Let's try 2 and 5. Okay, let's see if that works. We're going to FOIL it, right? And when you FOIL it, you get 3x times x is 3x squared. That part works. Then you do the outer. Ooh, minus 15x plus 2x. That's going to be minus 13x. Doesn't work. Guess what? Wrong number. Okay? Now, that sounded like a wrong number too, didn't it? Since it's a wrong number, let's swap the numbers. Okay? If it's a wrong number, change the numbers. Okay? So what we're going to do here is make this the 5 and that the 2. Okay? Change the numbers. See if that will work. It may or may not. This was 5. That's 2, right? All right. Now let's try it again. 3x times x? 3x. Yeah, that still works. 3x times minus 2? Minus 6x.
Plus 5x.
And that gives you?
Minus x.
Minus x. But the number's right. The sign's wrong. So if the sign's wrong, change the sign. Okay? So let's go back and make this the plus and make that other the minus. Okay? We'll try it one more time. Okay? 3x times x. 3x squared. 3x times 2. 6x.
Minus 5x.
Minus 5x is plus x. Minus 10. Yes, we finally got it right. That's trial and error. You try something that makes sense, but if it doesn't give you the right answer, then adjust it. Okay? Now, we still haven't found the zeros. What do we do now? Set each of those equal to 0. Let me get my pen back. Okay? So either 3x minus 5 is equal to 0, or x plus 2 is equal to 0. Because if two things multiply to be 0, one of them's got to be 0. Well, at least one of them. Maybe both. What do we do here? Now it's your turn. Add 5 to both sides. Right. For a linear equation, that's what you do. Okay? And what does that give you? 3x equal 5.
X equal minus 5 over 3.
Yes, divide both sides by 3. And that gives us x equal 5/3. We found the 0. Okay, how about this one? Yes, subtract 2 from both sides, x equals -2. Perfect. Now, I like to make sure I got it right. I just am picky that way. So let's try. Oh, this is tough, isn't it? Okay, let's start with the square. 5/3 squared is
25 over 9.
25/9. Multiply that by 3, and that becomes
75.
no 25 over 3. Make it simpler, not harder. Okay, you
25.
divide out 25/3 plus 5/3. Well, 25/3 plus 5/3. What would that be? 25 plus 5. 30/3, which is 10. Minus 10 is 0. Yes, that works. Okay. How about minus 2? -2 squared is 4 times 3 is
12.
Plus a minus 2 is
10.
10. Minus 10 is 0. Yes, we found the 2 zeros. And since this is a quadratic, you can't get more than 2 zeros. You cannot. The maximum exponent is the maximum number of zeros you can get. We found them. There they are. Okay? Now, let's do we have time to do the next one? Yeah. No? Huh? How much? 3 minutes? Don't you think we... Well, maybe not. Okay, we'll pick up next time with the B, but this gives us some more homework exercises. Yay! All right. You can do either 7 or 9. This is on page 56. They're both at Calc Chat. 9's at Calc View. Then you can do either 11 or 13. They're both at Calc Chat. 11's at Calc View. And then you can start doing 15 through, wow, I would say 15 and 17. Do those two. We'll come back and do the rest of them later. Okay? Make sense? And we still have time, don't we? No, I'm just kidding. All right. All right, I'll let you go a little early, but no refund. Okay? Stuck with it. All right, good deal, folks. Have a good weekend. Of course, working pre-calculus problems will make it good, won't it? Yes. Okay.
Okay.